Before we talk about the biology of how sound is perceived, let's first understand the nature of sound itself. A sound wave is produced when something vibrates and causes a disturbance in the surrounding medium. For us, usually air, but sometimes also water. This disturbance creates oscillating variations in the density and pressure of air at a given point at a given time. And these disturbances are transmitted through the air, much as ripples and waves travel through water. It's important to note that for sound, the medium itself, in this case air, isn't transported from point A to point B. That'd be wind. Rather, the disturbance and its energy are what's transmitted across space. Sound is produced when something vibrates, causing variations in the air pressure around it. If you look at a speaker playing loud music, you can get a glimpse of this physical movement that causes pressure waves in the air. The low bass sounds are caused by comparatively slow movements of the speaker diaphragm that are slow enough for us to see. When, for example, the speaker pushes the air molecules repeatedly, they become compressed and then decompressed or rarefied to generate a pressure wave that travels through the air. This kind of pressure wave, where the density of the medium is what's varying, is called a rarefaction wave. These waves travel at the speed of sound to our ear, where they cause the eardrum to vibrate, which ultimately generates the first neuronal activity. Here on Earth, the speed of sound is around 343 meters per second, or 767 miles per hour, but it varies with altitude and temperature at that altitude. That's pretty fast in the scheme of things, but glacially slow compared to light, which transmits effectively instantaneously. In contrast to photons, which are the fastest moving thing in the known universe, sound waves are only sort of fast. Man-made objects are routinely able to travel faster than sound. For instance, you might have heard of fighter planes that can fly at speed of Mach 2, which is twice the speed of sound. You can also get a sense of the comparative slowness of sound by watching lightning and listening for the thunder sound that it produces. Depending on how far away the lightning strike was, the thunder sound can take seconds to reach your ears, well after the photons have arrived. Almost anything can move air molecules to generate sound. The vibration of a guitar string, the soft humming of a songbird, our vocal cords, or the loud explosion of fireworks. Imagine all of these examples, and you'll notice a few distinct qualities of sound. First, sounds can be either loud or soft, depending on the amplitude of the pressure variation. A loud sound wave has a large amplitude because it's produced by large vibrations and large variations in air pressure. In contrast, soft sound waves have smaller amplitudes because they're produced by smaller vibrations and consequently smaller pressure variations. Second, sounds can vary in pitch based on the frequency of vibrations. A high-pitched sound comes from a high-frequency sound wave. When a speaker vibrates very rapidly, it produces a series of closely spaced pressure waves. In contrast, a low-pitched sound comes from a low-frequency sound wave, generated by slow vibrations and more widely spaced pressure waves. Humans can typically hear at a frequency range of 20 to 20,000 vibrations per second, also known as Hertz, named after the German physicist Heinrich Hertz. A person's hearing range declines with age, and as you get older, it becomes more and more difficult and even impossible to hear sounds above a certain frequency. Thankfully, only a very small range of frequencies are used in human speech, from about 200 to 2000 Hertz. So this normal age-dependent decline generally doesn't affect our ability to hear others talking. While humans do amazing things with sound, such as communicating through speech, the actual hardware of our ears isn't so remarkable. A number of animal species can hear frequencies well beyond the human range, and in many cases with much greater sensitivity. We can hear up to about 20,000 Hertz, but dogs can hear up to 45,000 Hertz, and cats up to 64,000 Hertz. Dolphins and bats can hear frequencies even higher, up to 100,000 Hertz. In the next few sections, we'll walk you through a general plan for how sounds are converted into neural activity.